Welcome back to ECE 501B. Today what I want to do is, well, next Monday we won't be here physically. Is that true? I made the assignment and I forgot that the 7th is Labor Day, but that's when I'm making it due, is at 11:59 that evening. You'll have all day to work on it, but I wouldn't start it that morning. I would maybe start on it now, or maybe in the past, maybe you already have started on the assignment. I'm not saying read chapter 2, I'm saying study chapter 2 relative to the kind of material that you're reading. It's more than just reading. You're actually trying to work through or understand the material as you go. Today what I want to do is pick back up where we left off by reviewing subspaces. Then we will define what's meant by a vector space sum in contrast to union of sets. Subspaces are different from sets. And then we will talk about a vector space direct sum, and that's different from a vector space sum. It has some unique properties or characteristics. We will look at some examples and then present propositions, and these are all relative to the second edition. Now, as it's becoming a custom, the first part I'm going to quickly slide through, meaning I already have pre-done some of this to hopefully get us through the material a little more quickly at the front end, and then we will slow down not too long into it. But first, before we start building with subspaces, we want to be able to sort of identify particular subspaces and then put them together and take them apart in certain ways. Before we do that, let's just review this idea or concept of a vector space. For U to be a subspace of a vector space V, and now you can be thinking in terms of 2D or 3D, you could say, okay, let's let V be a plane, and now maybe U is going to be a subspace of that plane. What properties need to hold for U to actually be a subspace? U must be a subset of V. That's different than a subspace. Let's say we had a two-dimensional plane. I could say a subset of that might be the integer coordinates. That's a subset, but that's not a subspace because it's not closed under scalar multiplication. If we took a real number at a constant that's a real number, we could make that constant 1.5, for example, and now that throws us into a location on our two-dimensional plane that's not an integer point. We could have a subset that's not a subspace. Is that clear? And U must satisfy not YOU, but the letter script U, or the capital U, this is our subspace, needs to satisfy all the properties of a vector space. Now, like we talked about last time, if U is a subset of V, then just because U is a subset of V, it inherits a lot of the properties of the underlying vector space V, just because it's a subset. Because of that, we only really need to verify 3 different properties on U that will make it be a subspace. So if you're checking to determine if this subset is indeed a subspace, then you simply need to check these 3 properties. One is that the subset contains the 0 element. Typically that's going to be the 0 or the origin, but we have seen vector spaces where the 0 element is not necessarily 0, or the origin. Then it needs, then it needs to be, wow, I think I just lost us in the classroom, but not. We need these three properties. And the last two are these closure properties. It needs to be closed under addition, and it needs to be closed under scalar multiplication, where the scalar multiplication is such that we pick a scalar from a field and use that to do a scalar multiplication on a vector, and that result of scaling that vector needs to remain in that subspace. Those are the three properties that we need to check. Let's look at some examples of subspaces. Here's the plane, and we know two right away. One is just the origin. That could be a subspace of R2. The entire plane could be a subspace of R2. And all lines passing through the origin are valid subspaces. It could be the x-axis, it could be the y-axis, it could be any line at a given angle going through the origin. Pictorially, here are a couple of subspaces. And you can see, I hope, that if you start on the x-axis and you take another vector on the x-axis and add those, you'll remain on the x-axis. So now the question is back to example 2 in the subspace of R2. Is it really a subspace if it's itself? And by definition, we're allowing that to be a subspace. So it may not be a distinct sort of reduction. It could be the entire space, and it's still called or constitutes a subspace of R2. Which means then that we could have, and we'll get there in a minute, but we could have the x and y directions as a subspace of R2. Here we simply are looking at the x-axis being one subset, but it's also a subspace of R2. The y-axis is a subset. This 45-degree line, it has equal coordinates, forms a subspace in R2. What are some cases that are not subspaces? And this is the same example. I just wanted to sort of have a second page on the same vertical piece of my screen. Now I have a line that's parallel with the x-axis. That's not a subspace. It's a subset. It is a set within R2, but now because it doesn't go through the origin, or it doesn't have a zero element, it does not constitute a subspace. For example, if we said, can we find a z that lives in U such that that z plus u will give us back u for any u? And you might think, well, let's pick this point. Let's say that, what did I say it is? Let's say that this is vertically up 1 unit. So now we are at points that have coordinates of y equal to 1. Maybe your first thought would be, well, sort of the zero element on that line is the point 0, 1. It has an x value of 0. But if you add 0, 1 to 2, 1, then you actually obtain 2, 2, which isn't on or doesn't have a vertical displacement of 1, so it's not in U. We can't find a 0 element in that subset that has all points at vertical distance 1. And the reason is it's not going through the origin. That subset is not a subspace. Trying to give you some ideas, some sort of counter examples of what does not form a subspace. And here is another one, a little bit less complicated than the one where I have all two-dimensional integer values. Now I'm just saying, suppose U is the subset of integers on the x-axis. That's obviously a subset of R2, but it does not form a subspace because it's not closed under scalar multiplication. We can pick a scalar that's real, let's say 1/2, and maybe our U is 3, 0. Then we would not end up with something that's an integer when we scaled it by this non-integer scalar value. That particular subset is not a subspace. And we can extend what we just talked about in R2 to R3. We can have the origin. We can have the entire three-dimensional space. We could have lines, one-dimensional subspaces, and we could have two-dimensional subspaces, which are now planes. But all of those lines and planes, in order for those to be subspaces, need to pass through the origin in our three-dimensional space in order to form subsets or subspaces. Are there questions on these examples? Let's now slow down a little bit and start talking about combining subspaces. And first, let's make it clear that now this concept of unions and summations are different. Unions of subspaces are not the same as the sum of subspaces. For example, let's look at two subspaces. Let's say U is one subspace, and let's let that be all points on the x-axis. U can be any real number, and the subspace only possesses non-zero coordinates in the x coordinate. And let's let V have non-zero second coordinates. And I'm trying now to distinguish distinguish between the union of U or of U and V and the sum of U and V. Graphically, if we looked at the union of U and V, I hope that it's clear that now we just, here's U, and here is V. And the union are just those two I shouldn't say direction, those two lines. The union is just the x-axis and the y-axis, nothing in between. We're just taking the union of those two subspaces. That's different than if we said, what if we combine those by summing the two elements in the different subspaces. Now if we look at x and y, is it clear that the sum I can get anywhere in x and y, which is different from taking the union of u with v? If that's understood, let's now start talking about sums of subspaces. Suppose we have a collection u1, u2, u sub m of subspaces, and they are all subspaces of V. Then the sum of subspace 1, 2, up to subspace M is defined to be the set of all possible sums of elements contained in U1, U2, U sub n. Symbolically, what that's saying is if we want U1 plus U2 plus all the way up to U sub m, that's the same as saying we have U1 as a vector in U1, etc. That's what we mean by the sum of these M subspaces. We can take any vector in U1, for example, add that to any vector in subspace capital U sub 2, and that is what we mean by the sum of those M subspaces. Let's look at some examples. Suppose we let script U be, let's say, U1, 0, 0. That's in R3, such that U1 is any real number. And let's let V be V1, V1, comma 0, also a vector in R3, such that V1 is any real number. And now let's look at S, which is the sum of U and V. S now is this set of U1 plus V1, comma, V1, comma, 0 in R3 such that U1 is real and V1 is real. But what is that equivalent to? You could view it simply as the XY plane in R3 such that X is equal to U1 plus V1 and Y is equal to V1 again where maybe I should have given myself X is real and Y likewise is real. So that this now becomes the XY plane. So that's an example of a sum of two subspaces where they don't have to be orthogonal or disjoint except for the origin. They could have some elements in common, so to speak. We are also interested in cases where our underlying subspace, capital V, is filled up by the sum of a finite number of subspaces, where now I'm saying V, the underlying subvector space, is covered by this combination, or I should say sum, of M subspaces U1 through U sub M. Now, that's what we are a lot of times interested in. We want our subspaces to completely fill or cover the underlying vector space. We also are interested in the case where this is a direct sum. So now let's define that. V is the direct sum. So our underlying vector space is the direct sum of U1, U2, U sub M. And we will actually establish some specific notation for that, written as V is equal to U1 plus with a circle around it, U sub 2, U sub M, if each element of V can be written uniquely as a sum U1 plus U sub 2 plus U sub M, where each of these U sub I, little U sub i's, are in the, or coming from, the subspace capital U sub I. Meaning we want to be able to represent any element in V as a unique sum of elements coming from those little m subspaces. Let's look at some examples. Suppose we have capital U, and now I'm going to write my vectors vertically instead of as rows. Suppose this one is now U00, 0, where we have a real first coordinate, or the first coordinate is any real number, and the second and third coordinates are nulls, or 0. Let's say y, script y, is now 0, little y, 0. Or now the first and third coordinates are 0, and the second coordinate is any real number. And I think you can see where I'm going with this. Now that's supposed to be a capital script W is equal to, first two coordinates are 0, and the last coordinate, or the third coordinate, is real. Now, is it clear that the three-dimensional space V, R3, is the sum of U, Y, and W? And in fact, it's a direct sum. Any point, let's say X, in R3 can be uniquely written as some combination of vectors coming from each of those three subspaces. In this case, V, which is all of R3, is U plus Y plus W. Now I don't want, yes, question? So you can think, the question is, should we be thinking about direct sums like partitioning? And yes, we are partitioning our underlying vector space into pieces, and those pieces are subspaces. In this particular example, those pieces are orthogonal, but they don't have to be. A direct sum does not have to be an orthogonal decomposition of our underlying vector space. So the subspaces do not have to be orthogonal to provide a direct sum. Let's look at an example of that. Suppose that U is now U first coordinate, U second coordinate, 0 third coordinate is a 3 vector where U is real. Suppose Y is 0, Y, 0. A 3 vector. And suppose W is 0, 0, W. where the third coordinate is any real number. That combination of three subspaces does fill R3. Our vector space V is all of R3, which is U, direct summed with Y, direct summed with W. Meaning for any X, any vector in our vector space capital V, let's say X now has coordinates X sub 1, X sub 2, X sub 3. If we now linearly combine subspace U or some subspace U, Y, and W, or vectors in that, we would have U plus Y, and W. So that now if we're given an X, we could actually let W just be X sub 3. We now need to find these unique combinations of U, Y, and W or vectors in those subspaces. We could do that by letting W equal to X3. That's going to define the vector in W subspace. We could let U be equal to X1. That's now going to specify this vector in script U subspace. That's this 45-degree line in the XY plane. And then we can let Y be X sub 2 minus X1. Again, we were given X1, X2, and X3. We now want to find a unique combination of vectors in U, Y, and W such that we end up with the X that we wanted to represent. So now Y would be some combination of the original X that we were given, since if we look at X2, that's equal to U plus Y, and we've already specified U, which was X1 plus Y, and now we can just solve for Y to obtain X sub 2 minus X1. So now we've specified W, U, and Y in terms of the given X1, X2, and X3. And that's a direct sum decomposition of R3, where now we didn't have orthogonality because there is some, what do I want to say, overlap between U and Y. We now have things that are 45-degree lines and Y, but those two vectors, when summed, can span the entire XY plane. Sure? So let me see what you're saying. You're giving me a vector X. And what is the vector X? So here's a question, Q. X is 2. Whoa, what are you giving me more for? 0, 5, 0? Pardon? So you're giving me U, Y, and W. And what was W? Oh, so you're now questioning, so now you have 110, and what are you asking? So I'm not seeing 274. If you have this one as 004, what am I missing? So I now see 174 down below and 274 up above. Is that okay? So now you have two sets of numbers. You were trying to show that you could get the same, let's say, final vector in V with two different representations from X, Y, and W. I can't remember what I'd labeled my subspaces as. So the idea is good. You're trying to now find where's the uniqueness. That's what we're trying to say in this direct sum is you can or you can represent any three-dimensional point in R3 uniquely from these three subspaces, which allows us to say that's a direct sum decomposition of R3. Is that clear? So the idea was good, but I think we just lost track of that 2 in the first X, and that's distinct from the 1. Now, we're going to get there in sort of another way. The easier way to think about this is not to come up with an X and stymie the process. The idea is to actually just say, can we write the origin as two different combinations in our sets? And if we can, then those are in our subspaces. Then those subspaces would not be forming a direct sum decomposition. So we'll get there in a minute with one of our propositions. But let me try to get over another example. So now I've looked at R3 so far, and all of my decompositions have been three subspaces. They wouldn't have to be. Suppose my first subspace is UV0, which is in R3, where U and V I can select independently. What is U pictorially? That's the plane, isn't it? That's the XY plane. That's coordinate 1, coordinate 2's plane. And now W is what we've been using. Let's just let W be a vector in the Z direction. Is it clear that those two create a direct sum decomposition of R3? So now I have another question. You guys are wearing me out. I didn't start on a good note. Now you will stump me. What? So now W is not contained in U, right? W is in the Z direction. I mean, you can find the zero vector in W. You can find the zero vector in U. They have to be there because they're subspaces. But now if you put any little bump in W, it's in a direction that's not in the same direction as U. Is that another way of saying they're separate? Now let's look at some propositions that allow us to think about these directs these direct sums. Pardon? Well, let's look at these propositions, because these propositions are going to tell us sort of what happens with these direct sum decompositions of vector spaces. So the propositions, and I think it will start talking to with respect to some of these intersections. So now the propositions will help us determine if a collection of subspaces is in fact a direct sum. And one of the key questions is, can the zero vector, and now you might want to expand this and say the zero element, can the zero vector, whoops, let me just say that. Can the zero element be represented uniquely by vectors u1 and script u1, u sub 2 and script u sub 2, little u sub m and script u sub m. That parenthetical second is the second edition of the textbook of Axler. Proposition 1.8, suppose capital U sub 1, U sub 2, on up to U sub m are subspaces of our underlying vector space V. Then V is a direct sum of U1, U2, up to U sub m, if and only if A, V is completed or filled up by the sum of these lowercase m subspaces, and B, the only way for U1 plus U sub 2 plus U sub m to equal the zero vector is for U sub I, each of those vectors in the sum are 0 for all U sub I in the M capital subspaces, where this, whoops, upside down A, I think I've defined it before. I'm using that to denote for all. So let's look at, we've been looking at positive results. Let's look at a negative example of a direct sum, or basically not a direct sum. So here is a negative example of a direct sum. Suppose U is now U1, 0, U sub 3, a vector in R3, such that U1 and U3 are real, and they're independent of each other. So now this is the XZ plane, is one way of thinking of script U subspace. Script Y is, let's say, V sub 2 in the second coordinate, or now the y-axis, and suppose that script W is this sort of 45-degree line in the XZ plane. And now we want to check, is V, which is all of R3, is that a direct sum combination of U direct summed with Y and direct summed with W? And in fact, I think you can see now, if we just look at what we have U1, or I'm sorry, subspace U is the XZ plane, subspace Y is the y-axis, and subspace W is this line going through the origin that is at a 45-degree angle in the XZ plane. We want to now ask, basically, if we combine those. So we had U1 and U sub 3, that's U. We had W, and we had Y. Now what we want to do is say, can we find the origin 0, 0, 0 in more than one way by some combination of U1, V2, U3, and W3? And this gets back to an earlier question where you were trying to find a particular vector. Now let's just pick the vector as an easy one, which is the origin, and say, can we find two sets of vectors in our subspaces that we can now let equal 0? Now, in this case, if we say for any x in R3, we can write that as x is equal to x1, x2, x3, and that's U1, 0, U sub 3, plus 0, V sub 2, 0, plus W3, 0, W3, and we could actually make that vector x out of the first two, couldn't we? If we simply said, let's let W sub 3 equal to 0, I still have the flexibility to get to any point in 3 space by U1, V2, and U3, since U1 and U3 in whatever I called it, U, were independent of each other. And so this now gives us U1, V2, U sub 3. And if that's not sort of convincing enough, that's sort of getting any vector x. Let's now look at just concentrating on a specific x being the origin. So let's now say, if we look at the origin, suppose we say here's 0, 0, 0, and all we have to do for a counterexample is find one counterexample. Suppose we now say here is a vector in U. Here U1 and U3 I just happen to make the same. And suppose this is now in Y, and let's make this in W. So here, this is an element in U. Here is an element in Y, and this is an element in whatever I called the last one. Was it W? But I can also create that 0 vector, 0, 0, 0. That vector is also in U. This vector is again in Y, like it was upstairs. And this vector is also in W. So I've now found two ways of representing the 0 vector from those two or three different subspaces. Or 0 can be written in more than one way. Or another way of saying that, 0 is not uniquely defined from U, Y, and W. And because of that, therefore, U, Y, and W do not form a direct sum of V equal to R3. And that was proposition 1.8, that we can only represent the 0 vector by picking all of our elements or vectors in the subspaces to be these 0 elements in those particular subspaces. And we actually found some non-zero vectors, which when combined will give us the 0 element. Let's look at proposition 1.9, which is another proposition that relates or talks about these direct sums. Suppose subspaces U and W are in our vector space V. Suppose U and W are subspaces of V. Then the direct sum of U and W is equal to V if and only if the sum of U and V complete the vector space. We can get to any point in V by a summation of vectors in U subspace and the W subspace, and the intersection of U with W the only point in common is the zero vector. That's another way of thinking about subspaces that form direct sums. They have to complete the space, and if we looked at their intersection, the only intersection in common or any vector in common is the zero vector. Is it clear what 1.9 is saying? That's what I just tried to communicate. The two subspaces U plus W need to fill all of our vector space V but their only subspace in common is the origin or the zero vector. Questions on that? So now, are there questions? That's basically what I want to cover in chapter 1 of Axler. Let's now start in chapter 2. So now when you start reading, maybe you'll have a little bit more insight into what's going on. So chapter 1, yes. So direct sum is not really saying linearly independent because of what did we have before? We haven't really talked about linearly independent, and that's what we're going to be talking about in chapter 2. So well, in a way, yes, it is, because you're kind of saying what's the only way that you can sum. So the linear independence concept we haven't yet had. So I guess what I'm trying to say is we were trying to define these direct sums without having to refer to something that we're going to talk about in chapter 2. But yes, getting ahead, we are looking at needing this independence of subspaces in some way, and the only place that they overlap is at the origin. But we weren't trying to say that because we hadn't yet discovered or defined those concepts. So chapter 2 is going to be talking about those issues in terms of span and dimension and linearly independent vectors. So what we've covered so far is just this very broad concept of vector spaces. That's chapter 1. Now, if we remember what we were doing in chapter 1, we weren't restricting that discussion to being finite dimensional necessarily, although my examples with combining subspaces have been with finite subspaces, but the vector space concept was not restricted to being finite dimensional. But to continue now with the yellow text or with Axler, we're going to concentrate or focus our attention on finite dimensional concepts, so that now we can branch off of vector spaces and we could go one direction and say, suppose we restrict our attention to concepts that are finite dimensional. That now brings us into this discipline of linear algebra, which is where we are going in chapter 2. If we went the other direction, and went infinite dimensional, then we would be seeing that termed something else in, let's say, the literature. That might be referred to as functional analysis in contrast to linear algebra, and that's the second textbook of the class, which is the Frank's textbook. And there you can think of these functions, continuous functions, differentiable functions, or functions that are continuous after differentiating those a number of times, etc. That's now functional analysis. Let's look at this left path and get into chapter 2 of Axler, which is the finite dimensional vector spaces. And what we're going to be talking about now is span, linear independence, and dimension. So let's first talk about what we mean by span, and that's an N, not an M. So this is, we're not filling up your inbox. In the past, that wasn't even an issue, that wasn't even a part of the definition of spam. Spam came in a little can. Maybe that's more than, well, I think as students, maybe you did or do know what spam is. But this is span. This is given a list of vectors. And what is the definition of list? It's finite, right? A list is finite. So whenever we use the word list, that means we're restricting our attention to a finite set. So given a list of vectors, let's say v1, v2, up to v sub little n, and let's say that we've pulled those or drawn those from a vector space. Capital V, the span of the list is the set of all possible linear combinations of the vectors in the list. And the notation that we will use is that the span of this list, so now span has an argument, and it's this list of vectors v1, v2, v sub n, that's defined to be a1 v1 plus a sub 2 v sub 2 plus a sub n v sub n, such that a1, a2 are any scalars from our underlying field of numbers f, where f could be real numbers or complex. That's what we mean by the span of these vectors v1 through v sub n. Let's look at an example. And we're giving things that are, I hope, somewhat visual or intuitive. Suppose we're given the plane, the xy plane, or R2, and we're given v1 of 3, 3, and v sub 2 of 4, 5. What do we mean, or what is the span of the two vectors v1, v2? What can we cover, or where can we go in the xy plane using these two vectors v1 and v2? Pardon? We can go anywhere we want in R2, and here's the thinking. If you were to simply look at this, and hopefully my sketch is somewhat to scale, I'm going 3, 3. There's this vector v1, and v sub 2 is over in the x direction 4 and up 5 in the y direction. They are not too different, but they are not aligned, are they? So we can, because there is some distinction in those vectors, we can linearly combine those however we want in order to cover the entire two-dimensional plane. Where our solution would be as follows. The span of v1, v2 is a1, v1 plus a sub 2, v sub 2, where we're taking a1 and a2 to both be any real numbers. So now we could have a1 scaling 3, 3, and a sub 2 scaling 4, 5. So that now we have 3a1 plus 4a2 and 3a1 plus 5a sub 2, such that a1 and a sub 2 are any real numbers. And what you've told me is we can cover any point in the in R2. So this should give us any coordinate z1 and any coordinate z sub 2 by the choice of a1 and a2 is what you're telling me. If we can get anywhere in the xy plane, that means you can give me any z1 and any z2 And I can find an A1 and an A sub 2 that will linearly combine 3, 3, and 4, 5 to get you to that point. And that's what I'm doing. I'm letting Z1 be 3A1 plus 4A sub 2. And Z sub 2, I'm letting that be 3A1 plus 5A sub 2. So that Z1 and Z2, which is any arbitrary point in the plane, I can write that equivalently as 3A1 plus 4A2 and 3A1 plus 5A2 for the two coordinates, or that's 3, 4, 3, 5, A1, A2. Do you see that I think in terms of linear algebra? So now I have some matrix times A1 and A2, and now I can solve for A1 and A2 because I remember how to invert a 2 by 2 matrix. Meaning you give me Z1 and Z2, I can multiply that by this 2 by 2 matrix and give you the values for A1 and A2. Or A1 and A2 are 1 over the determinant of that matrix, which is 3 times 5 minus 3 times 4, or 15 minus 12, or 3 in the denominator. And I can interchange my diagonal entries and negate the signs of my off-diagonal elements in the 2 by 2 matrix to then give me this relationship of 1 over 3, 5 minus 4 minus 3, 3, Z1, Z2, or that's now 5/3 Z1 minus 4/3 Z sub 2 minus Z1 plus Z sub 2 is how I can now select A1 and A2 given Z1 and Z sub 2. You could also do two equations in two unknowns and solve that however you want without having to do this matrix inverse. And I hope that I've now convinced you that given any point in the plane, Z1 and Z2, you can now find how to scale 3, 3 and how to scale 4, 5 in order to get there. And we'll pick up, that's talking about span. We'll talk about linear independence and dimension on Wednesday.